Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
Modern VLSI design involves the development of complex high-speed digital integrated circuits containing millions of transistors and timing paths. In synchronous digital systems, both functional correctness and timing correctness are essential for reliable operation. Even a logically correct design may fail if the signals do not propagate within the required timing limits. Therefore, timing characterization and timing verification play a critical role in determining the overall performance and reliability of the chip. Static timing analysis, or STA, is one of the most important verification methodologies used to analyze and ensure correct timing operation in modern VLSI system design. In this video we will have a review of the fundamentals and basic concepts of static timing analysis. So, let's get started. The figure shows a typical synchronous timing path of asynchronous digital systems. In synchronous circuits, all data transfers occur with respect to a common clock signal. For reliable operation, data must arrive and remain stable around the active clock edge. If flip-flops do not satisfy setup and hold timing constraints, metastability or incorrect operation can occur. The combinational logic between flip-flops introduces propagation delay that directly affects timing behavior. Therefore, correct logical functionality alone is not sufficient unless the design also satisfies timing requirements. Static timing analysis helps verify that every timing path in the design operates safely within the specified clock period. Static timing analysis, commonly called STA, is an important verification methodology used in modern synchronous VLSI system design. It checks whether digital signals travel through different circuit paths within the required clock timing limits. STA analyzes timing behavior mathematically without depending on input test patterns, making the verification process faster and more efficient. It evaluates the delays contributed by logic gates, interconnects, and sequential elements to ensure reliable circuit operation. STA helps designers detect timing violations, critical timing paths, and clock-related issues early in the design cycle. As modern chips contain millions of timing paths, exhaustive simulation-based timing verification becomes extremely difficult and time-consuming. Therefore, STA is widely used during synthesis, placement, clock tree design, routing, and final sign-off stages of chip implementation. It also considers the impact of process variations, voltage fluctuations, temperature changes, and interconnect parasitics on circuit timing. By ensuring that all valid timing paths satisfy setup and hold constraints, STA improves chip reliability and performance. Thus, static timing analysis has become one of the most essential verification techniques in high-speed digital VLSI design. As shown in the flow diagram, the static timing analysis begins at the gate level. Using standard cell libraries to estimate delays before physical design. In physical design, static timing analysis evolves from ideal models to highly accurate delay estimation. During floor planning and placement, timing is evaluated using estimated wire loads and library-based cell delays. As routing progresses, interconnect resistance and capacitance begin to dominate overall path delay. Parasitic extraction introduces detailed RC values, significantly improving delay accuracy. Back annotation feeds these extracted parasitics into timing analysis for realistic path evaluation. At this stage, STA captures the impact of slew, load, coupling, and PVT variations on timing. Finally, sign-off timing ensures that all paths meet setup and hold requirements with maximum accuracy. The figure shows the synthesized gate-level netlist transformed into a physical layout through placement and routing across the chip area. This physical realization introduces real interconnect delays, parasitic, and loading effects impacting timing behavior. Within this layout, 4 primary timing paths are identified: input to register, register to register, register to output, and input to output paths. Among these, the register to register path is the most dense and critical, forming the backbone of synchronous timing analysis. These paths traverse the core area, interacting with clock distribution, cell placement, and routing congestion. As a result, variations in delay, slow, and coupling effects are most prominent in register-to-register paths. Therefore, STA focuses heavily on these paths to ensure setup and hold timing closure across the design. In asynchronous digital systems, the clock defines when data is launched, propagated through logic, and captured by flip-flops. Without proper clock synchronization, data may arrive unpredictably, leading to timing errors or metastability conditions. Timing verification ensures that all the timing path constraints are met. Dynamic timing verification uses input test vectors, simulates the circuit and observes the behavior over real time. It provides realistic waveform analysis but cannot be repeatedly carried out. Whereas STA mathematically analyzes all timing paths, without requiring simulation vectors, and offers faster analysis, wider path coverage, and can be repeatedly used throughout the design flow. However, STA for correct verification results depends on accurate timing models, identifying and specifying the timing constraints. Together, static and dynamic verification methods ensure reliable, high-speed, and robust operation of synchronous digital systems. The images shown represent the major timing paths encountered in a logic design. Clock gating paths use logic gates to control clock-enable signals for reducing power consumption. These gated clock paths must be verified carefully to avoid glitches and incorrect clock operation. Asynchronous paths originate from signals such as reset or preset that bypass normal clock synchronization. The clock path distributes the clock signal to all sequential elements and directly affects synchronization and clock skew. The clock period determines the required arrival time. The data path is the actual path that transfers data between an input and output pins, passing through sequential and combinational logic gates. The path element's delay determine the actual arrival time. Therefore, data propagating time along with the corresponding clock period determines the timing path performance. The images illustrates the 4 major timing paths present in a synchronous logic design. The in-to reg path transfers data from an external input through combinational logic to a capturing flip-flop. This path is important for validating input arrival timing with respect to the system clock. The reg2 out path propagates registered data from a flip-flop through logic to an external output pin. This path ensures that output data is available within the required output timing specification. The in-to out path directly transfers input data to output through combinational logic without intermediate registers. This path is commonly used in combinational or bypass logic sections of the design. The reg2-reg path transfers data between 2 flip-flops through combinational logic and is the most critical timing path in STA. It determines the maximum operating frequency of the design and must satisfy both setup and hold constraints. Among all these paths, the reg2-reg timing path is the most important because it defines the core synchronous operation and performance of the digital system. The text shown briefly describes the 4 data timing paths as shown in the previous slide, namely, the register-to-register path. This path mainly determines the maximum operating frequency and overall chip performance. The others timing paths are input to register and register to output timing path that have to satisfy external input and output timing constraints. The input to output path is a purely combinational path, without any sequential elements or clock storage devices. For reliable synchronization, and proper functionality of the digital VLSI design. These timing paths together have to ensure correct data transfer. This slide illustrates the register-to-register, or reg-to-reg, timing path, which is the most important path in synchronous digital systems. Data is launched from the source flip-flop at one clock edge and captured by the destination flip-flop at the next clock edge. Between the two flip-flops, the data propagates through combinational logic and interconnect routing. The timing performance of the path depends on flip-flop delay, logic delay, routing delay, and clock distribution delay. The path must satisfy setup constraints so that data arrives before the next active clock edge. It must also satisfy hold constraints to ensure that data does not change too early after the clock edge. Clock skew, clock uncertainty, and process variations strongly influence the timing margin of this path. Static timing analysis verifies whether the path operates safely under worst-case timing conditions. Reg-to-reg paths determine the maximum operating frequency and overall performance of the chip. The clock source fans out through buffers, forming a balanced clock tree that drives synchronous elements. This distribution network ensures uniform arrival of the clock edges across the chip grid. In a reg-to-reg data path, from the launch flip-flop, the input data is registered and sent forward into the combinational logic. The data path propagates through logic gates whose delay must align with the clock cycle. At the capture flip-flop, the arriving signal is sampled against the distributed clock edge. Phase delay and skew are minimized by careful buffer placement and routing symmetry. Static timing analysis verifies that the reg-to-reg path meets performance requirements under all operating conditions. The clock period defines the fundamental cycle time against which all data paths are measured. Waveform integrity ensures clean transitions, avoiding distortion that could compromise timing margins. Uncertainty from skew and jitter represents variations in edge arrival that STA must account for. Latency, both source and network, reflects delays in clock distribution across the chip. Transition times, whether at inputs or clock edges, influence setup and hold requirements. Propagation delays through logic and interconnect add to the total path timing budget. Static timing analysis combines these parameters to verify slack and guarantee reliable synchronous operation. Flip-flop operation requires both before and after the clock transition, the input data to remain stable. Before the clock edge, the already arrived data must be present and stable for at least the setup time, period, allowing the internal latch structure of the flip-flop to latch the input data. After the clock edge, already received data must continue to remain stable for, at least the hold time. Ensuring that the captured value is reliably transferred and, stored internally, without getting disturbed from a new incoming data. Therefore, for successful operation of a flip-flop, setup and hold are not two isolated events but form one continuous stability requirement around the clock edge. This complete interval extending before and after the clock edge is called the timing window or data valid window of the flip-flop. This waveform illustrates the setup timing analysis of a reg-to-reg synchronous timing path. Data is launched from the source flip-flop FF1 at the active clock edge. The launched data propagates through the clock-to-queue delay, combinational logic delay, and interconnect delay. The total propagation delay forms the actual arrival time, or AAT, of the timing path. The destination flip-flop FF2 must capture the data before the required setup timing limit. The required arrival time, or RAT, is determined by the clock period, setup time, clock skew, and clock uncertainty. The difference between RAT and AAT gives the setup slack, which indicates the available timing margin. This slide explains the hold time verification of a reg-to-reg synchronous timing path. Hold time is the minimum duration for which data must remain stable after the capture clock edge of the destination flip-flop. The hold check is always measured with respect to the same clock edge that captures the data. After capturing the data, the destination flip-flop requires a short interval to safely lock the received value. If new data launched from the source register propagates too quickly through the logic and interconnect path, it may overwrite the previously captured data before the flip-flop stabilizes. This results in hold time violation, incorrect circuit operation, or even metastability conditions. Therefore, hold timing analysis ensures the stability of already captured data rather than checking the arrival timing of new data. In a reg-to-reg timing path, data is launched from the first flip-flop, travels through the combinational and interconnect network before reaching the second flip-flop. The earliest arrival time at the capture register is defined by the minimum clock-to-queue delay of the launch register combined with the minimum logic delay. The required arrival time is determined by the hold time of the capture register together with any clock skew between the launch and capture clocks. Hold slack is then calculated as the difference between actual arrival and required arrival, showing whether the timing requirement is met. A positive slack means the hold condition is satisfied, zero slack means the path is exactly balanced, and negative slack indicates a violation where data arrives too early. This analysis ensures that sequential circuits remain stable by preventing premature data capture and maintaining reliable operation across registers. The figure illustrates the input-to-register timing path of a synchronous digital design. The incoming data propagates through external combinational gates and at the active clock edge is captured by the destination flip-flop. The actual arrival time includes input or external arrival delay, combi logic, and interconnect delays. The required arrival time is determined from the clock period, setup time, and clock uncertainty. Slack is calculated as the difference between RAT and AAT logic delay, net delay, clock skew, and jitter are the major contributors affecting slack. Positive slack indicates safe timing operation, while negative slack indicates timing violation. The sequence of steps in a reg-to-out timing path operation is as below. The clock signal travels through clock tree, clock buffers, and the clock edge triggers the flip-flop. The launched data propagates through flip-flop, combi logic, interconnect and external load and reaches the output. At the output pin, the arrival time equals the sum of all path delays from the clock edge. The required arrival time is set by the clock period minus the setup time. Slack is the difference between required and actual arrival times and indicates the margin or violation. Positive slack means timing meets the requirement, negative slack flags a reg-to-out failure. The image illustrates the in-to-out timing path of a sequential digital design. Data enters from an external source and propagates through combinational logic and reaches the output. No flip-flops are present in this path, making it a purely combinational timing path. Although no registers exist, clock-related system constraints still influence the timing requirements. The path performance depends on logic delay, routing delay, and external loading conditions. Maximum delay constraints ensure that output data reaches the destination within the required time, which is one or multiple clock cycles. In-to-out timing paths are widely employed in interface logic, and timing verification ensures reliable external data transfer and correct system-level operation. Process, voltage, and temperature, PVT, variations arise from manufacturing tolerances, supply fluctuations, and environmental conditions, and they directly influence MOSFET electrical characteristics. Process variations change parameters such as channel length, oxide thickness, and threshold voltage, leading to faster or slower transistors. Voltage variations affect the drive current, where reduced supply voltage lowers switching speed while higher voltage increases speed but may raise power consumption. Temperature impacts carrier mobility, with higher temperatures generally reducing mobility and increasing delay. These variations alter the switching behavior of MOSFETs, which in turn affects the delay, power, and reliability of logic gates in the standard cell library. As a result, the same gate can exhibit different timing characteristics under different PVT corners. This variability impacts overall circuit performance by shifting timing margins and potentially causing setup or hold violations. Therefore, STA must consider multiple PVT conditions to ensure robust and reliable operation across all scenarios. Logical design rules, LDRs, such as fan-out, maximum load capacitance, and transition time arise due to the finite drive strength and intrinsic resistance, capacitance behavior of CMOS gates. As more loads are connected or interconnect length increases, the effective capacitance seen by a gate grows, leading to slower charging and discharging of nodes. This results in increased propagation delay and degraded signal transitions, directly impacting circuit speed and timing margins. Excessive fan-out or load can also cause poor logic level integrity, making signals more susceptible to noise and reducing reliability. Slow transition times further increase short-circuit power and can adversely affect the performance of downstream gates. These effects collectively degrade overall system performance and may lead to timing violations in critical paths. Therefore, adhering to logical design rules is essential to maintain predictable timing, signal integrity, and robust circuit operation. Various other factors that also impact the timing path performance of the design are, as discussed below. Clock behavior introduces challenges such as skew, jitter, and uncertainty, often worsened by improper clock tree synthesis or imbalance in distribution, while multi-clock domain synchronization adds further complexity. Logic gates contribute excessive combinational delay and high fan-out loading, with timing variability across standard cell libraries. Process, voltage, and temperature variations, along with power supply fluctuations and IR drop, directly affect gate delay and circuit stability. Asynchronous crossings risk metastability, while glitches and hazards in combinational logic threaten reliable signal propagation. Finally, incorrect or missing path exceptions and timing constraints can mislead analysis, making static timing verification incomplete. As technology shrinks, the interconnect parasitics play a significant role, and some of the critical effects are as follows. Interconnect routing delay and parasitic RC effects increase sharply, leading to maximum capacitance violations on nets. Slow signal transitions or slew rate violations become more common, while cross-stalk noise between adjacent interconnects threatens signal integrity. Long critical paths with excessive logic depth add latency, while short data paths risk hold violations. Poor placement and routing further amplify wire delay, compounding timing challenges. Together, these factors highlight how interconnect parasitics dominate performance in advanced nodes, demanding precise analysis and optimization to ensure reliable operation. Summarizing so far covered, static timing analysis is one of the most fundamental verification techniques in modern digital VLSI design. It helps ensure that high-speed synchronous systems operate reliably under all timing conditions before fabrication. By understanding timing paths, timing constraints, and slack behavior, designers can identify and correct potential failures early in the design cycle. STA enables faster, more reliable, and optimized chip implementation in today's complex semiconductor technologies. With this background, we can explore further relevant topics like path exception, principle of static timing analysis evaluation system, slack computation by graphical method, fixing of timing violations, etc. Thanks for your time. Hope this presentation has provided STA basics, required for appreciating the significance of timing analysis in the VLSI design. In the upcoming video, we will continue with further topics on STA verification. Thanking you once again and hope to meet you in the upcoming video. Bye for now.